Okay, so lesson number 6 looks at geometric growth and decay. So there's a lot of patterns that exist in science that have geometric growth and geometric decay. Bacteria cultures tend to grow geometrically. And we talk geometric growth this year, next year we move it into an equation and we talk about it in terms of exponential growth and exponential decay. So the Globe and Mail published an article in 2010 stating that the University of Victoria is struggling with an out-of-control rabbit population. At the time of the rating in 2010, there was an estimated 1,500 rabbits on the U of Vic grounds. So if the rabbit population increases at a rate of 20% per year, complete the table below to give an estimate for the number of rabbits in 2011, 2012, and 2013. So I have 1,500 in the first year. How do I figure out the amount in the second year? Tell me what you're doing. So Jessica multiplied by 1.2. Is that what you did, Rachel?
Well, I multiplied it by 0.2 and then added it to 1,500, but that's just more sense.
Yeah. So multiplying by 1.2 is actually the same as the two steps that you were talking about. So if I multiply by 1.2, how many in 2011?
18.
And 2012?
2,160.
And 2013?
2,500.
So you have a growth of almost, well, more than 1,000 rabbits in a 3-year time span. Okay. This is just the growth rate. It doesn't take into account what the mortality rate is. So it wouldn't necessarily mean that you would have. You could have up to this many rabbits. Chances are you wouldn't, because there would be natural dying off, natural selection. So show that the sequence representing the rabbit population is geometric and state what the common ratio is. So to prove that it's geometric, what you have to do is prove that if I take any two terms and divide them, so 1,800 divided by 1,500 equals 1.2. Or 2,160 divided by 1,800 would also equal 1.2. Or 2,592 divided by 2,160 would still equal 1.2. So if the first term of the sequence is the number of rabbits in 2010, which term of the sequence represents the number of rabbits in 2025? So this is the first term, the second term, the third term, the fourth term. So in 2025, how many terms will I have traveled? 16 terms, good. So if the population grew at a rate of 20% and we don't take any other factors into consideration, how many rabbits would I have on the university grounds in 2025? So my T of n formula, which is A times R to the power of n minus 1. A is my first term, which was? R is my common ratio, which was my 1.2. And in 2025, there's 16 terms. So tell me what you get. What'd you get, Bobbiana?
23,110.53236.
So 23,000 111 rabbits. So in this question, the geometric growth factor is the common ratio. It is what I'm growing by each year. So in this example, the geometric growth factor is 1.2. So that's geometric growth. Geometric decay is going the opposite way. Vinny borrows $10,000 from his parents to buy a car. His parents lent him the money interest-free as long as he makes a payment at the end of each year. They agree on a repayment schedule, which results in Vinny owing 10% less at the end of a particular year than at the beginning of the year. This repayment scheme lasts for 8 years. At the end of the 8 years, he makes one final payment to pay off the loan. So at the end of the first year, how much money does he owe his parents?
Would be $9,000.
$9,000, okay? At the end of the second year, how much does he owe his parents?
$8,100.
The third year?
$7,290.
And at the end of the fourth year?
$6,516.
These values form a geometric sequence. Calculate the common ratio. So the common ratio I get by taking any two consecutive terms and dividing the first by the preceding term. So what is 8,100 divided by 9,000?
0.9.
That becomes my geometric growth factor, is 0.9. How does 0.9 fit into the context of this question? 10% off the 100. If it's 10% paid, that means that there's 90% remaining. So when I have a growth factor, I add it to 100%. When I have a decayed factor, I'm subtracting it from 100%. So determine how much he owes at the end of the 7th year. So at the end of the 7th year, that would be T of 7. My first term, what's A? 9,000. What's R? And then I've got 7 minus 1, so it's the 6th term. And what do I get? $4,782.97. So if my growth factor is between 0 and 1, I'm going to have geometric decay. So I just want to do class example number 3, and I'll save 4 for tomorrow. State the growth factor in each of the following situations. The rate of inflation is increasing by 3.5% each year. So what would my growth factor be?
1.035.
How did you know to add it to 1? What word? Increasing. The number of fish in a lake is decreasing by 2% a year. 0.98. Because that word decreasing tells me I'm going to be reducing it from 100%. The number of rabbits in a population doubles each year.
2.
Just 2. The value of a computer decreases by 1/5 each year. So if it decreases by 1/5, what's left? 4/5. Or as a decimal, 0.8. A ball rebounds to 3/4 of its previous height after each bounce. So how come this one I didn't subtract from 1? What makes this one, or what makes the wording of this one so different that in B and D I subtracted it by 1, but in E I just take the 3/4? What word? Say it.
Rebounds?
Rebounds. Rebounds means it comes up to that height. So it doesn't say it loses 1/4 of its previous height. It rebounds to 3/4 of its previous height. I think there is, question number 1 on the assignment is like this class example. So I want you to take a try at that one for tonight. Back to math class. Okay, consider the following problem. A rubber ball is dropped from a building that is 20 meters high. Each time the ball bounces, it bounces back up to 80% of its previous height. Calculate to the nearest centimeter the height of the ball after the 15th bounce. So Lucasito decides to solve the problem using a geometric sequence where t of 1 equals 20. Explain why the 15th term would not be the answer to this problem.
Because 20 isn't the first bounce, it's the height of the ball.
20 is not the height after the first bounce. Which means t of 15 would not be after the 15th bounce. It would actually be after the 14th bounce. So if I was to use his method, that would be t of n equals a times r to the power of n minus 1. A is the first term, or 20. What is r? 0.8. I don't have to take it away from 100 because it bounces back up to that 80% mark. And then n would be the number of terms, which would have to be 16. I would need 16 terms to get to the 15th bounce. So then I would get 20 times 0.8 to the power of 16 minus 1. And what do I get? So if I was to round this to the nearest centimeter, because this is in meters, what would that be to the nearest centimeter? 70 centimeters, thank you, Evan. Nicolette argues that the value of T15 should be the solution to the problem. If I'm going to calculate the height after the 15th bounce, I should be looking for the 15th term. So if Nicolette chooses to do this option, explain why the first term would not be 20.
Because that's the height that you start at. It's not after a bounce.
Because T of 1 has to be the height after the first bounce, which is not 20. What would the first term then be? What would be the height after the first bounce? 16 meters. So now if I use Nicolette's method, I get T of n equals a times r to the power of n minus 1. Her a is 16. Her r is still going to be the 0.8. But in this case, her n will be 15. The 15th bounce. So I get 16 times 0.8 to the power of 15 minus 1. And what do I get?
Oh, I get the same answer.
I get the same answer. So if I was to use a formula or an equation to represent the height after x bounces, for Nicolette, her formula for the height, so h equals, her a is 16 times 0.8. And so if she wanted to find the height after 7 bounces, her r value, or the exponent on her r value, would be 7 minus 1. So it would be the number of bounces minus 1. That would be Nicolette's. If I look at Lucasito's, the height for his would be starting at the 20 times 0.8. And then if I look at his, when it was 15 bounces, this value here ended up actually equaling 15. So if I had after 7 bounces, this would end up being to the power of 7. It would be the 8th term, but it would be the 7th bounce, or the exponent would be 7. So question D says, write an equation that can be used to determine the minimum number of bounces required for the rebound height to be less than 2 centimeters. So first of all, if I have 2 centimeters, my formula deals in what units? Nope. What was the formula?
Oh,
Meters. So I have to convert this into meters, which would be 2/100ths of a meter. So the equation that would be used to determine the minimum number of bounces would be my height would equal 0.02. And then I could use either Nicolette's or I could use Lucas's, although his, I don't have to worry about the x minus 1. So 20 times 0.8 to the power of x. So if we use our graphing calculator to do this, So if we're using the calculator to do this question, it would end up being, let y1 be equal to 0.02, and then my y2 be equal to 20 times 0.8 to the power of x. And then I need to do some adjusting on my window settings. So in my window, my x's refer to the number of bounces. Okay? And I know from previously that after the 15th bounce, the height was 70 centimeters. So I know I need to have more than 15 bounces, but I know I don't need negative bounces. So I could go up to 25. My height, what's the height that I'm trying to get or trying to see? It's that 0.02. So I don't need to have a great big height. I could even just start at 0 and go to 2 if I wanted to. And then my scale, I could just leave at 0.5s. If I put a scale at 0, it just draws a line. It doesn't put any tick marks in it. There's my 0.02. And I'm actually not enough. So I need to adjust the window settings again. Go up to maybe 30 this time. And that 200ths, I need this to be much smaller. So even if I went to 0.5 and then graphed it, now I can see a separation of the line. It doesn't just look like it's on the axis. Still doesn't look like it's crossing. So try again. Maybe go up to 40 this time. And you know what? I'm going to change this to be 1/10. And now I've got an even bigger gap so that hopefully I can see it actually cross the x-axis. Or sorry, cross the intersection point. So now that I have the intersection, I can use the Calc 5. And I don't actually have to scroll close to the intersection because there's only one intersection point on the screen. If I press enter, it'll go to second curve. If I press enter, then it'll say guess. I don't want it to guess, but it will eventually jump to here. So I get an answer of what? 30.956. Okay, so if we put that on here, I get that x equals 30.956. So what is the minimum number of bounces I need for the height to be less than 2 centimeters? Say it louder. 31 bounces. If this number here had been 30.32, how many bounces would I need? I would still need 31 because at 30 bounces the height isn't quite enough. And I could check that. If I used just the formula and I went 20 times 0.8 to the power of 30, I get 0.0247, which is about 2.5 centimeters. It's only when I put in 31 that it's below 2 centimeters, and that was the condition of the question. Okay? So then the last example. Mike invests $5,000 in a GIC, which is a guaranteed investment certificate. Each year, 3% interest is added to the value of the investment at the beginning of that year. Consider the geometric sequence which represents the value of the investment at the end of the year. So what is my growth factor? Would be the 3%, but then I have to add that on to the 100% that I already have. So I'd have the 100% of the investment plus the 3% interest, which when I convert to a decimal, I get my 1.03. That's my growth factor. B says write a product which represents the value of the investment after 1 year. This product will represent the first term of the geometric sequence. Don't evaluate this product at this time. So at the end of the first year, I would have my $5,000 and I would multiply it by that growth factor. That would be the value of the investment after the first year. What would I do at the end of the second year? How would I find the value of the investment after the second year?
And she just add another 1.0.
Yeah, I would just multiply by 1.03 again. Remember, it says do not evaluate. So D says use the formula T of n equals A times R to the power of n minus 1 to write an expression which could be used to calculate the value of the investment after 10 years. Simplify it, but don't evaluate it. So T of n would be what is the value of the investment after the first year? That was this right here. So that's my A value. A is equal to this 5,000 times 1.03. My R is equal to the 1.03. And my N value is 10, the value of the investment after 10 years. So T of 10 would be 5,000 times the 1.03 times the 1.03 to the power of 9. And if I simplified these two, the bases are the same, which means I can add the exponents. I end up with 5,000 times 1.03 to the power of 10. So question E says state the value of the investment after the first year, after the second year, and then after the 10 years. So after the first year, we just take it from what we had above. If I take 5,000 and multiply it by 1.03, what do I get?
5,150.
After 2 years, I would multiply it by 1.03 again. Or I could go 5,000 times 1.03 squared. $5,304.50. And then after the 10 years would be calculating out this expression. 5,000 times 1.03 to the power of 10. And tell me how much money you get. What'd you get, Evan?
$6,719.58.
So in 10 years, I gained just about $2,000 interest, or $1,700 interest. Use the general formula to write an expression that could be used to calculate the value of the investment after n years, and show that this could be written as a power with an exponent of n. So if I look at my general term, T of n equals A. From above, A was 5,000 times 1.03. And then R is 1.03. And then I have to the power of n minus 1. If the bases are the same, and I'm multiplying powers, I can add their exponents. The exponent here is 1. If I go 1 plus n minus 1, what happens to the 1s? Cancel each other out. They're going to equal 0, so I'll be left with n. So I get the equation 5,000 times 1.03 to the power of n. So then part G says, suppose that an investment earns interest of I% per annum. Develop a formula for the amount of the investment after n years, which is the compound interest formula. So T of n is the value of the investment at the end. That's my A. T of 1 is what I started off with. That's my principal, my P amount. And then I have my interest, which I'm going to take and I'm going to add it to 1. Or I guess, because I is given as a percentage, I have to divide it by 100 first. Like that. So I have to take my interest, convert it to a decimal, and then it would be to the power of n, just like what we did in this equation here. So we're going to look at this next year when we look at exponential functions, but this is the formula which comes from a geometric sequence. The big thing with the last two examples is just really understanding what it means for the first term in the context of a problem, because sometimes the first term is not what was given to you in the question. So in the previous question with the bounces, depending how you look at it, the first bounce is not necessarily the 20th, or the 15th, or the 15th term does not necessarily represent the 15th bounce. Did I give you any questions from this yesterday?
Question 1.
Just question 1? Okay. So then 2, 4, 8, and then 17, 19, and 20.